Why does a Toyota Crown taxi in Tokyo or a Honda commuter car in Japan routinely push past 500,000 miles on its original engine components, while the exact same badge in Western markets is often labeled finished before it even crosses 150,000? That gap isn't random, and it isn't luck. It's a pattern, one that quietly exposes how different maintenance culture, engineering priorities, and long-term reliability philosophies can shape the lifespan of the exact same machine. Most drivers are conditioned to believe that once an engine starts burning oil, losing compression, or sounding rough, it has reached its natural end. But what if that end isn't mechanical at all? What if it's the result of how the engine has been treated, what fluids it has been fed, and what assumptions have been repeated so often that they feel like fact? For decades, one of the most repeated habits in car ownership has been the short oil change interval, the familiar sticker telling you to return every few thousand miles. Yet modern engine design, improved machining tolerances, and advancements in lubrication chemistry have quietly evolved far beyond those older routines. In Japan's domestic market, manufacturers and fleet operators often follow longer service intervals paired with higher quality lubricants and stricter consistency in maintenance timing. The result is not just convenience, it's stability. Engines that operate with cleaner internals, more consistent lubrication films, and less thermal stress tend to degrade more slowly over time. Instead of cycles of neglect followed by sudden intervention, they experience steady, predictable protection. At the center of this difference is lubrication science, specifically how oil interacts with metal surfaces under pressure, heat, and motion. Modern engine oils are no longer just slippery liquids. They are engineered systems designed to reduce wear, manage temperature, suspend contaminants, and maintain protective films under extreme conditions. Additive packages, including friction modifiers and anti-wear compounds, play a critical role in how effectively that protection is delivered. When these systems are optimized and consistently applied, they can significantly slow the microscopic wear that gradually erodes engine components over hundreds of thousands of miles. But the story doesn't stop at chemistry. Driving habits, warm-up routines, fuel quality, and maintenance discipline all contribute to whether an engine ages quickly or slowly. Short trips that never allow the engine to reach full operating temperature, irregular oil changes, or the use of lower quality fluids can accelerate internal wear. On the other hand, consistent operating conditions, proper servicing, and attention to detail can extend engine life far beyond what most drivers expect. The difference between a worn-out engine and a long-lasting one is often the accumulation of small decisions repeated over time. So the real anomaly isn't that some cars last 500,000 miles. It's that more of them don't. When you look closely, the gap begins to make sense. It's not about a single secret or a hidden switch. It's about understanding how modern engines are designed to operate and aligning maintenance practices with that reality instead of outdated habits. What follows is a deeper look into those practices, the systems, routines, and engineering principles that quietly determine whether a car becomes scrap at 150,000 miles or keeps running long after most people would have given up on it. To understand what truly separates long-life engines from early failures, you have to step outside the automotive world and look at aviation. Jet engines operate under punishing conditions, extreme heat, constant pressure, and continuous stress that would break down conventional lubricants in a very short time. To survive this, engineers in the 1940s developed a different class of base oil known as ester-based synthetic lubricants. Unlike traditional mineral oils that mostly float between moving parts, ester molecules are polar, meaning they are naturally attracted to metal surfaces. This allows them to form a thin, consistent film that clings to components even when the engine is under stress or temporarily starved of oil flow. Instead of relying only on fluid thickness, this chemistry creates a kind of microscopic bonding effect that improves lubrication stability under real-world conditions. By the 1960s, performance-focused programs, especially in motorsports, began experimenting with these advanced lubricants. Honda, through its Formula One development efforts, leaned heavily into precision engineering and lubrication science, pushing for more consistent protection at high RPM and extreme temperatures. Over time, this approach filtered into consumer-level engineering philosophies in Japan, where durability and long-term reliability became core design priorities rather than afterthoughts. By the 1980s, companies like Ineos were already producing engine oils that blended synthetic esters with advanced additive packages, aiming to reduce wear not just for thousands of miles, but for the entire lifespan of the engine. One of the most important components in these additive systems is a friction modifier known as molybdenum dithiocarbamate. Under heat and pressure, this compound reacts at the surface level to form an ultra-thin, low-friction layer on metal components. This layer isn't permanent in the sense of never wearing off, but it continuously regenerates as long as the additive is present in the oil. The result is a dynamic protective barrier that reduces direct metal-to-metal contact, especially during cold starts and high-load conditions where most engine wear actually occurs. Compared to basic oil formulations, Systems that include effective friction modifiers and stable-based stocks can significantly reduce long-term wear rates. However, it's important to understand this as an engineering advantage, not a miracle shortcut. Modern high-quality synthetic oils, especially those designed with robust additive packages, are built to maintain viscosity, resist thermal breakdown, and protect engine internals for extended service intervals under normal driving conditions. Independent research in tribology, the science of friction, wear, and lubrication, has consistently shown that oil performance depends heavily on formulation quality, operating conditions, and maintenance consistency. Engines that receive stable lubrication with fewer breakdown cycles naturally accumulate less microscopic damage over time. What makes the difference in high-mileage engines is not a single additive or a one-time treatment. It's the consistency of protection over hundreds of thousands of miles. When lubrication systems are stable, contaminants are controlled, and wear is minimized at the microscopic level, the cumulative effect becomes visible. Cleaner internals, tighter tolerances, and longer-lasting components. That's why certain vehicles, including high-mileage examples like the Toyota Tundra, have gained attention for reaching extraordinary distances without major engine rebuilds. These cases are not magic. They are the result of disciplined maintenance, high-quality lubrication, and engineering designed to support longevity. So the real secret isn't hidden in a bottle or locked behind a price tag. It's in understanding how lubrication chemistry works, choosing the right oil for your engine, and maintaining consistency over time. When those factors align, engines don't just last longer. They age differently, resisting the kind of wear that most drivers assume is inevitable. The biggest obstacle standing between an average car and a 500,000-mile lifespan isn't some catastrophic design flaw. It's misunderstanding how maintenance actually works over time. One of the most common phrases drivers hear at dealerships is lifetime fluid. It sounds reassuring, almost like a guarantee that certain components don't need attention. But in reality, lifetime rarely refers to the full lifespan of the vehicle. It often aligns more closely with warranty periods or ideal operating conditions, not the long-term reality of heat cycles, contamination, and gradual chemical breakdown inside critical systems. Take transmission fluid as an example. Whether it's a traditional automatic or a continuously variable transmission, CVT, the fluid inside isn't just a lubricant. It's also responsible for cooling, hydraulic pressure, and smooth gear operation. Over time, that fluid is exposed to heat, microscopic metal particles, and oxidation. As it degrades, its ability to protect internal components declines. Regular drain and fill intervals, rather than waiting indefinitely, can help maintain stable performance and reduce long-term wear. This becomes especially important in vehicles like Nissan models equipped with CVT systems, where fluid condition plays a major role in how long the transmission continues to operate smoothly. Another area where confusion often arises is oil change intervals. Modern owner manuals sometimes recommend extended intervals under ideal conditions, which can be helpful for reducing maintenance frequency in the short term. However, real-world driving, short trips, traffic, temperature swings, often places more stress on engine oil than those ideal scenarios assume. Over time, oil accumulates contaminants, loses some of its protective properties, and becomes less effective at managing heat and friction. Drivers who prioritize long-term durability often choose more conservative intervals, along with high-quality filters and manufacturer-approved oil specifications, to keep internal engine conditions as stable as possible. Cooling systems are another overlooked factor in engine longevity. Engine coolant doesn't just regulate temperature, it also contains additives that prevent corrosion inside the radiator, water pump, and engine passages. As coolant ages, these additives can deplete and the fluid may become more chemically aggressive. Left unchanged for too long, this can contribute to internal corrosion or reduced cooling efficiency. Periodic coolant replacement, along with attention to components like the thermostat, helps maintain consistent temperature control and reduces the risk of overheating-related damage. What ties all of these systems together is a simple principle. No fluid lasts forever under real operating conditions. Heat, pressure, and time gradually change the properties of every lubricant and coolant in a vehicle. Relying solely on the idea of sealed or lifetime systems can lead to delayed maintenance, which in turn increases the likelihood of wear or failure as mileage accumulates. On the other hand, consistent preventative care, based on how the vehicle is actually used, can significantly extend the life of major components. Reaching extreme mileage isn't about ignoring manufacturer guidance. It's about understanding the difference between minimum requirements and long-term optimization. When drivers take control of maintenance decisions, adjust intervals based on real conditions, and treat fluids as critical components rather than permanent solutions, they move out of the short-cycle ownership model and into a long-term reliability mindset. That shift alone can make the difference between a vehicle that fades early and one that continues performing far beyond expectations. Reaching 500,000 miles isn't about chasing a miracle trick. It's about applying a consistent, disciplined system built on how engines actually behave over time. The Japanese method is best understood as a set of practical habits that reduce wear at every stage of the engine's life cycle. Step 1 begins with choosing the correct oil specification for your vehicle. Modern engines, especially those with emission systems like particulate filters, often require what's known as low SAPS oil, low sulfated ash, phosphorus, and sulfur. Using the wrong formulation can affect both engine protection and exhaust system health, so aligning with manufacturer specifications is critical before you even think about optimization. Step 2 is about timing and consistency. If you're using a high-quality synthetic oil or considering advanced additive packages, they should always be introduced during a fresh oil change, not midway through an old cycle. Clean oil allows the additive system to function as intended, forming a stable lubrication layer without interference from contaminants. This is where modern lubrication chemistry, including friction modifiers like molybdenum dithiocarbamate, plays its role, helping reduce friction and wear under heat and pressure. The goal isn't to coat the engine permanently, but to maintain a consistent protective environment every time the engine is running. Step 3 focuses on operating conditions immediately after maintenance. Short, varied driving, rather than idling or extremely short trips, helps bring the engine up to proper temperature and ensures oil circulates fully through all components. Most engine wear happens during cold starts, when oil hasn't yet reached every surface. By allowing the engine to warm up properly and operate under normal load conditions, you reduce repeated stress during those critical early minutes of operation. Over thousands of cycles, this small habit compounds into significantly less internal wear. Step 4 shifts attention to the fuel system, an area many drivers overlook. Running your fuel tank consistently near empty increases the likelihood of drawing in debris from the bottom of the tank and places additional strain on the fuel pump, which relies on fuel for cooling. Maintaining a healthier fuel level helps stabilize pump operation and reduces the risk of premature wear in injectors and related components. Long-term reliability often comes down to avoiding these small, repeated stresses that don't cause immediate failure, but slowly degrade performance over time. Step 5 is where discipline matters most, addressing minor issues before they grow. Small components like sensors, thermostats, or worn hoses may seem insignificant, but they directly influence how efficiently the engine operates. For example, a malfunctioning oxygen sensor can disrupt the air-fuel mixture, increasing fuel consumption and placing extra load on the exhaust system. Left unchecked, issues like this can cascade into more expensive repairs. Preventative replacement of low-cost parts, along with regular inspection, keeps the entire system operating within its intended parameters. Beyond the engine itself, environmental factors also play a role. In regions where roads are treated with salt, corrosion can become the limiting factor in a vehicle's lifespan. Protective measures like periodic cleaning and underbody treatment can help preserve structural integrity, ensuring the vehicle lasts as long physically as it does mechanically. In many high-mileage cases, the engine remains strong while the body deteriorates, highlighting how longevity is a full vehicle strategy, not just an engine-focused one. When you step back, the 500K blueprint is less about a single secret and more about alignment, matching maintenance practices with engineering reality. Drivers who follow consistent intervals, use the correct fluids, maintain stable operating conditions, and fix small issues early often see dramatically different outcomes compared to those who rely on minimum guidelines alone. Over time, this approach doesn't just extend the life of a car, it transforms how that car ages, turning what most people consider a short-term asset into a long-term reliable machine.